For the next part, we are going to introduce a new family of functions. So we defined elliptic functions and so meromorphic lambda periodic functions. But we said that there was no much interest in entire lambda periodic functions. So what we are going to define is lambda quasi-periodic functions. And in that case, we will be looking at the entire ones. So these will be theta functions and Abel's theorem. So we have seen now that given a lattice lambda in the complex numbers, there's a way of obtaining an elliptic curve E with E over the complex numbers being isomorphic to the complex lattice defined, but the complex torus defined by lambda. However, a simple implementation of this shows that it's not really effective. This we will see a bit in the programming exercises that we will have associated to this. We will compare different implementations to see what's a nice way of or efficient way of obtaining this elliptic curve. And so in this section, what we will introduce we consider a new type of function associated to lambda that will be much better for our goal. And that is what I said about quasi-periodic functions. So we say that a function f in the complex numbers is quasi-periodic with respect to lambda if there exists a function E that goes from complex times lambda to C such that f of z plus lambda is equal to this E at z lambda times f of z for all z in the complex numbers, lambda in the lattice. And this term here is what we call the automorphy factor of f. Okay, so why are these functions still interesting if we already looked through the elliptic functions? Well, it's because if we choose the right quotient of two of these functions, maybe we can make the automorphic factors cancel and we obtain meromorphic functions again, which would be great because then maybe we can write the Weierstrass function in terms of these. So the one that we will look into is the following. Let lambda in C be a lattice given by lambda generated by 1 tau with the imaginary part of tau being positive. So here is the first time where we actually really need this condition that we put on the lattice. And here we define that the theta function is given by z tau equal the sum over all the integer numbers of the exponential of pi n squared tau plus 2pi n z. It is a lambda quasi-periodic function with automorphic factor E of z a tau plus b equal the exponential minus pi a squared tau minus 2pi a z. And I really recommend that you take as an exercise the definition of the theta function and try to really prove that this is indeed the automorphic factor associated to this function. It's very nice way to get familiarized with theta functions to manipulate these sums, because it will come up in other situations. So we also will consider certain modifications of these functions. So for AB real numbers, we also define the theta function with characteristics AB as the sum theta, and now I will write AB as subindices of z tau equal the sum for n in the integers, and it's again expression quite close to what we just saw. So pi, and now here we have a plus n square tau plus 2 pi n plus a z plus b. So we have these a's and b's now added, and actually again another thing that you can try to prove by manipulating these sums this actually can be written as the exponential of pi I a squared tau plus 2 pi I a z plus b times the original theta function evaluated at z plus a tau plus b tau. So it's just a modification of evaluating this with respect to this extra element of the not the lattice, because we are taking coefficients in the reals, but with respect to the lattice. So it's like a translation with a certain automorphic factor in front. So this inherits, in a sense, the automorphy, like the lambda quasi-periodicity of the original theta function, and it gives us its own automorphic factor. So we'll get there in a moment. So the quasi-periodicity of theta, of the theta function, translates to the following. So now we are looking at what happens when we add an element of the lattice in the characteristics. So basically a plus p, b plus q as characteristics now, where p and q are integers, of z tau is equal to the exponential of xp I a q times the theta with characteristics ab of z tau for z in the complex numbers, ab real, and pq integer. So basically we cannot take AB in the complex torus because it's not an equality, but there's still again another automorphic factor here. So all of these functions are multivalued in the complex torus, right? Because again, in the complex, because we have this automorphy factor, different representatives of the same point in the complex torus will give us different values in the function, but the zeros are well defined. Basically because we don't really care about the automorphic factor in that case. So basically, if we have a zero in a point in the complex numbers, we'll have it for that for every lattice point. And the study of this family of functions is huge, and there are a lot of things that one can study about them. There are some relations that are satisfied for their products and their powers. They determine some embeddings into projective spaces. But for the sake of our goals, the result that we are interested in, we don't need to go into all that vast sea of knowledge. For the goal at hand, we focus on the family of theta functions with characteristics in 1/2 z squared modulo z squared. So of course, again, this is not well defined because we have this quasi-periodicity with respect to the characteristics, but we will just take the representatives that have the entries between 0 and 1. That gives us 4 possibilities. And we will denote them by the numerators with respect to this expression. So we will omit the divided by 2 in the sub-indices. So basically we have theta of 0, 0, which is simply the theta function normally, theta of 0, 1, which, yeah, theta of 1, 0, and theta of 1, 1. These are the 4 thetas that we'll be looking at, and one can prove, and again, I leave this as an exercise for you, is that that theta 1, 1 evaluated in minus z is nothing other than theta of 1, 1 at z for every z in the complex numbers. And the case where this becomes very, very relevant is when we take z equal to 0, because it just tells you that in particular theta 1, 1 at 0 is equal to 0. And this will be key for the next result that we will see. Okay, so it says there is a meromorphic function on C modulo lambda with zeros a sub I. So with the brackets I mean the class of the complex number a sub I in the complex torus of order n sub I equal I from 1 to n, and poles b sub I of order m sub I, j's, and the j now goes from 1 till m, even only if two conditions are satisfied. The first one is that the sum for I equal 1 till n of n sub I is equal to the sum for j equal 1 till m of m sub j. So basically it means, for those more familiar with divisor statements, that the divisor corresponding to this function is of degree 0, which makes sense because it has to be the divisor of a function. Okay, so as I was saying, we have this condition, and the second condition is actually that the sum for I equal 1 till n of n sub I a sub I is equal to the sum for j equal 1 till m of m sub j b sub j. So as a point in the So a point in the complex torus, we need this equality to hold. So and one can think, okay, so can you now think of a function that satisfies this? Well, we know that, sorry, there's a function. Yeah. We also have that, moreover, it is unique up to a constant. So what that means is that if we are able to come up with such a function, then we have found it up to a constant multiplicating in front. So for example, and what can we take now? Well, g of z equal, do we know of any function that has a 0 in a particular place? Yeah, we just talked about one, right? We have theta 1 of 0 in the definition before. So that means that we can take for I equal 1 until n theta 1 1 of z minus a sub I. Observe that now we are not taking the class anymore, because that would not be well defined because of the quasi-periodicity. Now we are taking one representative. And it's okay as long as we use them consistently. So we have this on the numerator, on the denominator, j equal 1 till m theta 1 1 of z minus b sub j m sub j. And this will have exactly zeros at a sub I of order n sub I, and poles at b sub j of order m sub j. So this is up to a constant, the function that is that satisfies the hypothesis of the theorem. So that's nice, because we have these functions, and these functions, I haven't mentioned it, but they converge very quickly when you try to compute them numerically. So ideally, we would like to use this theorem to write the Weierstrass function. And that will prove to be a bit more tricky than one would initially expect, because the zeros of the Weierstrass function are not easy to write. Let me write this. Ideally, we would but as I was saying, the zeros of the Weierstrass function are not easy to write in terms of the lattice. So this is not the right approach. The trick then will be to find the right function to try to express in terms of this. And it has to do with something that we have already defined before, which is choosing the right representation of the elliptic curve. So let me explain. Okay, let me go back to what we have seen so far and try to summarize the situation where we are at. Again, so let lambda in C be a lattice with, and we take it in the shape that we defined before, so generated by 1 tau with the imaginary part of tau positive. Let E of lambda be the elliptic curve. And here we take y squared equal 4x cubed minus g2 of lambda x minus g3 of lambda. So recall this is the definition that we obtained from the relation satisfied by the Weierstrass function. And what we want to consider now is actually the factorization of the right-hand side. So here we obtain 4x minus e1, x minus e2, x minus e3, where e1, well, yeah, we just factored this and we obtained this equation. What's interesting now is that actually the points that have by x coordinate e1, e2, e3 are what we call the Weierstrass points of the curve, what also means that they are 2 torsion points. Let me explain this with a drawing. So if you remember, I'm still going back over the real numbers because it's just easier to draw there. So we have this elliptic curve, and what would be that point? Actually, if I take the other shape, it works better. What we can also take as an elliptic curve has this shape. And now the 3 roots that we are drawing there are this point, and this point. And what do I mean by saying that these are 2 torsion points? Well, I mean that if I write pi to be the point ei0, then pi plus pi, or what we would write with elliptic curve notation like 2pi, it's just the point at infinity. Because if we try to look for a line that passes twice by this point, it's just the tangent line, and it's vertical. So it means that the third point of the curve in the line is the point at infinity, and the line that goes through the point at infinity twice actually cuts the elliptic curve on the point at infinity a third time. So basically, this is exactly what this means, if you remember the definition of the addition that we saw in the introduction. Why is that relevant? Because looking at torsion points on the lattice, it's much easier. So we haven't actually drawn many lattices so far. Let me do it now. Okay, we have here the complex plane, and we have a certain lattice. I make it big enough so that we only see 4 points in this image. I hope it's kind of straight. Anyway, so here we have, when we take a complex lattice, what we have is like this type of grid that is given by our 2 periods. So this is 1, and this here is tau, my complex point, and this defines what we call the fundamental region of the lattice. Okay, and basically when we take the complex plane and quotient out by lambda, what we are doing is like cutting this rectangle and identifying this side with this side and this side with this side, and this way we recover the torus shape, the donut shape that we had at the beginning. And now if we look at this, we have that the points that represent the point at infinity, or the identity for our addition, are in this case the points of the lattice. So this point, this point, this point, this point, etc. So now if we try to look at what points satisfy that when you multiply them by 2, you get the identity point. In this case, it's very easy. You just have to go to halfway there. So basically, we have tau halves, 1/2, and tau plus 1 divided by 2. These are what will be the 2 torsion points of the complex torus. And that also works if we now think of the isomorphism that was given by the P function, right? So the points E1, E2, E3 will be the images of the P function at 1/2, tau halves, 1 plus tau halves. We can assign them without loss of generality because we can always reorder them if necessary. So we have P1, P2, P3 are 2 torsion points. And E1 is equal to the P function evaluated at 1/2. E2 is equal to the P function evaluated at tau halves. And E3 is equal to the P function evaluated at tau plus 1/2. Okay, so once we have this, we can consider the change of variables that hopefully you obtained when you were looking into the isomorphism that links the Weierstrass form with the Legendre form. Okay, so what are we doing with this change of variables? Well, the divided by 2 is so that we remove the 4 that we had as a coefficient that didn't really match the Weierstrass form. And for the rest, this is the P1 isomorphism that sends E1 to 0. So when we evaluate this at E1, we get 0, and the denominator is different from 0, because one can actually prove that these 3 values are different. If we evaluate it at E2, we have the same on the numerator and denominator, so we get 1. If we evaluate it at E3, we get a certain expression that's what we call lambda, and the point at infinity stays at infinity. So that's good. So this gives the isomorphic model y squared equal x minus 1, x minus lambda, with lambda equal E3 minus E1 divided by E2 minus E1. And this is the function that we will now write in terms of thetas. How will we do that? Well, we can consider the following function. And we take f of z equal the p function at z minus e1, or what's the same, the p function at z minus the p function at 1/2. Why is this function interesting? Well, because if we look at lambda, it's just f of z evaluated at tau plus 1 divided by 2 divided by f of z evaluated at tau divided by 2. Okay, why am I interested in this function? Well, it has very nice properties. We have that it is a meromorphic function with double zeros at 1/2 plus lambda. Remember when I said that the p function cannot really be written in terms of, its zeros are not easily written in terms of lambda? That stays true, but the thing is that by taking a translation, now we know for which values of z we have a 0. So that's exactly for the values that are 1/2 plus a point in the lattice. And because this translation doesn't affect the poles stay in the points of the lattice. So now, these conditions, characteristics or conditions of the function are satisfied the assumptions in Abel's theorem. So we have that up to a constant, there's a unique function that has double zeros at the points 1/2 plus lambda and double poles at the points in the lattice. And we know that function up to a constant because we saw it in the theorem, right? So we have f of z, it's no other than a constant that we don't know times theta 1, 1 at z minus 1/2 squared divided by theta 1, 1 at z squared. So yeah, this is the AI, which is 1/2. The exponent is 2 because we want double poles. Double zeros. We want double poles at 0 plus the lattice. So we have this expression, and because it's double, we have the exponent. And then, as I wrote before, we can write lambda as a quotient of the image of two of these. So that will make the constants disappear. Okay. So what I will do now is to look at how we can write this in the nicest way possible. It's, again, some tinkering with the theta constants. So that's why we wanted all that practice before. I will do now explicitly the computations for the numerator. For the denominator, you can just go ahead and do it yourselves using the same ideas. So we have the theta 1, 1 of tau minus 1 divided by 2. Sorry, am I writing this? Yeah. So now, I'm looking first, at the denominator here. And we have that theta 1, 1 of tau minus 1 divided by 2. So that will be what we have in the numerator of this expression. Let me write the middle step first. So f of tau divided by 2 is no other than c theta 1, 1 tau half minus 1 half squared divided by theta 1, 1 of tau half squared. So now we get a bit of tinkering with numbers. So theta 1, 1 of tau minus 1 divided by 2. Here we first use the definition of this theta function with characteristics 1/2, 1/2. And we get 3 pi I tau divided by 4 times theta of tau minus 1/2 divided by 2 plus tau plus 1 divided by 2. So here what we have used is that theta 1, 1 of z tau is equal to, and we just have to take the definition of this transformation of the theta functions that we had, and this gave us for these characteristics the following factor. I'm omitting the tau because we have fixed it at first. I've actually been doing this for a while now. But the original function was like this. But okay, so once we have this, we can just rewrite it, and we have the thing that we have here, it's just tau. So now tau is an element of the lattice, so we can use the quasi-periodicity to remove it from there. And I'm going to do it here so that we have some space. And now theta of 0, it's just the theta with characteristics 0, 0 at 0. So I'll take it just for the subindices. And if I simplify the expression, the factor in front, okay. So that's what we would obtain on the denominator there. We can do the same for the numerator. I will give a bit less details now. So at tau divided by 2, we obtain 3 pi I tau divided by 4 plus pi I 2 theta feel free to let me know through the platform where I have a typo, because I'm sure there's one. You can try to find it. With these things, you always have to recheck your computations 3,000 times before you can actually keep them. So here, before we got theta of 0, now we have theta of 1/2. So actually we can use now the theta functions with characteristic 1, 0 as subindices to rewrite this, but that adds a new factor, which in this case is 1, so we are good. And what we obtain in this case is minus pi tau divided by 4 minus pi divided by 2 theta 0, 1, 0. So we have again the theta function evaluated at 0 with a certain subindices. So now if we put it all together, and I think I will just use this corner of the screen. So all together, we obtain f of tau divided by 2 equal minus c theta 0, 0, 0 squared divided by theta 0, 1, 0 squared. Analogously, one can do the same thing for the other part of the expression. And we obtain that f of tau plus 1 divided by 2 is equal to minus c theta 1, 0 square divided by theta 0, 0 square. Let's put all the squares on the same side here. And we just now need to take the quotient to obtain the expression for lambda. And I will do that in the other board. So finally, we obtain that lambda of lattice lambda, it's just theta 1, 0 to the 4th, sorry, 0, 1. Theta 0, 1, 0 to the 4th. Sorry, there's typos everywhere. Okay. Oh no, actually this is correct. Oh no, here. These two subindices go swapped. So it's the 1/2, the one that we have here, and it happens again in the other case. Okay, so when we do the quotients, if I didn't write anything wrong, we should get exactly, that's the denominator. Sorry, yeah, it's the other way. It's a bit tricky always to use all these characteristics. But the summary of all these tinkering with theta functions is that we can actually write the lambda in the Legendre form of the elliptic curve in terms of the thetas, and because thetas have much better behavior convergency-wise than the sums either in the Weierstrass function or in the coefficients g2, g3 of the equivalent equation, this allows us to find an isomorphic model in a much more efficient way. And this is what we will use in the next session to actually be able to construct lattices that give us complex torus with interesting properties, and then obtain the elliptic curve associated to such lattice. Okay, so for the last section of this session, what we are going to see is how to use this effective way that we have found of computing an elliptic curve associated to a certain complex torus, and we will use it to find some curves with some interesting properties or good properties. So let me give some definitions. let E be an elliptic curve, and let lambda in C be a lattice such that the set of complex points of the elliptic curve is isomorphic to the torus given by this lattice. We will write that we have then that the endomorphism ring of the elliptic curves, that is the homomorphisms of the curve onto itself, it's isomorphic to the complex numbers that map the lattice into itself. So this we will see that it's exactly what we will mean by having homomorphisms over complex toruses on the next session. Yeah, and the ring here is independent of the choice of lambda, so it doesn't really matter in that. This ring. And we can have one of two things. Well, we already talked a bit about the multiplication by Nmap on elliptic curves. We will see it a bit in more detail when we talk in the next session about abelian varieties. But we saw it when we were talking about the two torsion and the Weierstrass points, that of course if we have an addition, we can also just multiply a point by an integer, and it will be nothing more than adding it as many times as set integer. So we will always have that this ring contains all the integers. In fact, what we have is that either the endomorphism ring is exactly the set of integers, or the field generated by attaching the period of the lattice to the rational numbers is an imaginary quadratic extension of Q, and then the endomorphism ring of the associated elliptic curve is isomorphic to an order in this quadratic imaginary extension. So let me go a bit over the proof. You can find it written with more formalism in one of the references that I will put. So let lambda be a lattice, and we write it with respect to our choice of period, and we write R to be just the complex numbers such that they map the lattice to the lattice. So for any alpha in R, there exists A, B, C, D on the integers, such that we can write alpha as A plus B tau and then alpha tau is c plus d tau. And so we can eliminate tau from the equation using the system. We obtain, well, alpha square minus a plus d alpha plus ad minus bc is equal to 0. So R is an integral extension of the integers, because this will be the minimal polynomial for the value of alpha, and it's a integer harmonic. So R is an integral extension of z. And now if we assume that R is not exactly the integers, so now we want to be on the second case of what we had here. We eliminate, well, first we assume that alpha, we have taken it in R but not in the integers, so in whatever it's left, it follows that b is different from 0 in the way that we took alpha here. So if we eliminate alpha from the system, we get that b tau square minus a minus d tau minus c is equal to 0. And so that means that T defines a quadratic extension, and it's imaginary because tau we know it's not real, so that it can define a lattice on the complex numbers. And R is integral in this extension, so we have that it's an order. So this completes the proof. And what is nice about this, and we can see very well in this genus 1, dimension 1 case, is that the fact that this lattice has extra, or that this curve has extra and homomorphisms or endomorphisms, it basically means that in the lattice they show up as extra symmetries of this set. So have a look at the complementary materials that are shared in the platform to see some examples of lattices associated to elliptic curves with complex multiplication. We will see the different axes of symmetry, and I think that gives a nice motivation to why this is a case that we might be interested in. So what all of this means in practice is that to construct an elliptic curve E such that the endomorphism ring of E is isomorphic to Z mod square Z D, it is enough to take Z sub D, the right tau sub D, the right element, on Q of square root minus D, and compute lambda evaluated at this point, using here the expression of lambda in terms of theta functions that we gave in the previous section. Two things. First, here I'm saying that we take tau D to be the right element. In general, in the more general case, it will be the square root of minus D. In some cases, depending on the value of D modulo 8, we have some other expressions. We will see this in a more general setting in the last session of the course. For now, I will just give you a table of which is the appropriate tau D to give. So we have D mod 8, and we have tau of D. So if D mod 8 is 1, 2, or 5, then we just take square root of minus D. If it's 3, we take 3 plus square root of minus D divided by 2. If it's 6, we take 3 plus square root of minus D. And finally, if it's 7, we take minus 3 plus square root of minus D divided by 2. So this is the way that we choose tau D to do these computations. So one last result that or property that I want to give about these elliptic curves with complex multiplication . Theorem. E has complex multiplication if and only if J of E is an integer, an algebraic integer. Okay, so this result we will see very soon why it is important, but it will be key if we want to obtain an exact model for the curve. And that's simply because as we saw, the theta functions are given as an infinite sum, and of course we don't have the time to compute an infinite sum. So we will have to stop at some point, and then the only thing that we will obtain is a numerical approximation of lambda, which has much precision as our patience gives us. So I will show this just with an example. We take k equal q of I, the Gaussian, it will give us that the endomorphism ring for the associated elliptic curve that we obtain, it's just the Gaussian integers. The period matrix that we have to choose. And for this we look at the table. D in this case is 1, so we just take tau equal I. Then we compute. And I will write a lot of decimals just so that it's nice. Of course, this you do it with a computer. You don't have to write so many numbers, but the theta function with characteristics 0, 0, evaluated at 0 for the period I, it's just the sum for n in z of e to the minus pi n square. Of course, as I was saying, this is an infinite sum. We don't have the time for that, so we will stop at some point the addition. I decided to stop when I had a very long number, 3, 5, 7, 9, 1, 3, 8, 1, 5, 6, 1, 1. If we look at this series with enough care, we could actually bound the error that we are doing by choosing a certain truncation point, and that will be relevant for the last step. Here I won't go exactly into the details of that. I will just mention it out loud because it's important to have these details in mind. So in this case, pi n plus 1/2 square, and this is isomorphic to 1,086,434,811,21,33, and the last is a 0, so I won't copy it. So with this result we obtain lambda at the period I is equal to 0,4999, a lot more 9s, 852, and that the J invariant at I is equal to 172800, lots of more zeros, 4542. But if we know that we have enough precision in these computations, if we know that we have enough precision in these computations, we can say that instead of saying that J is this decimal number, we could give J as an interval, considering this error, and that if we have an interval that is small enough, this will contain only one possible integer. So that allows us to say that indeed this lattice corresponds to, sorry, this is an approximation. So because we know that the J invariant is an integer and it's very close to this number here, we conclude, let me write on the other board because this is the last thing. So if we can guarantee the precision of our approximation, we obtain that by the previous theorem, J of I is exactly 1728. So the isomorphism class of the elliptic curve E with E of C isomorphic to C to the G modulo IZ plus Z is that of y squared equal x cubed minus x. And this is very nice in dimension 1. It will not be so nice in higher dimension because we won't have this theorem that tells us that the invariant is an integer, but we will find ways around it. For now, just take into account that there are some details to deal with. How can we guarantee a certain precision here so that we can guarantee that in the interval that we have, the arithmetic error interval that we have for here, there's only one integer so that we can actually claim that that's the J invariant, the exact J invariant. We will do that in some of the more advanced exercises associated to this session, so be sure to check that. We will be using Sage Math for that. And that's everything that I had to say for today. Thank you.